Hello everyone. My name is Kinal Mehta and I am an MS student at IIIT Hyderabad. Today I will be talking about how spectral normalization helps in learning in sparse rewards cooperative multi-agent reinforcement learning. This is a joint work with Dr. Anuj Mahajan and Professor Pawan Kumar. Before I go into exactly how to do that, it is important to understand some of the background and motivation. And common challenges in RL include exploration, sparse rewards, and partial observability. Challenges of multi-agent RL include exponential growth in joint action space with increasing number of agents and non-stationarity introduced due to learning co-players. When we have sparse rewards in multi-agent environment with large number of agents, it becomes really challenging to learn for standard algorithms. We focus on cooperative multi-agent reinforcement learning. Cooperative MARL problems are formulated as decentralized POMDP or DEC POMDP. State-of-the-art solutions use centralized training, decentralized execution paradigm for solving these cooperative multi-agent environments. VDN, QMix, and MAPPO are typical examples of CTDE-based approaches. DEC POMDP is defined by the given tuple consisting of environment state S, action space of each agent U, the transition matrix P, the reward, which is common to all the agents R, local observations of agent Z, which is sampled according to the observation function O, given the environment state S and the agent ID I. Now, let us say tau I be the action observation history of agent I, then we define the decentralized policy as pi I, which predicts ui given tau I. And the objective is to find decentralized policies which maximizes the team reward or team return. PPO is a single agent actor-critic algorithm which optimizes for a clipped objective with scale penalty. Here, the clipping is done based on hyperparameter epsilon, and the KL penalty is for how divergent is the latest policy from a specific held out policy. MEPPO is a multi-agent extension to PPO with centralized critic, which is used to learn the value function. Spectral normalization is a regularization technique which regularizes the weight matrix of a layer by its largest spectral value, constraining the layer to be one Lipschitz continuous. It has been used in GANs to prevent mode collapse and discriminators. In context of single agent reinforcement learning, it has been used in DQN and DDPG. We are the first to use it in the context of multi-agent RL and on-policy RL. Now, let us look at our method and experiments. We use Robotics Warehouse and StarCraft multi-agent challenge environments for evaluating our proposed method. RWARE is a simple sparse reward multi-agent environment where the agents have to collect the re- required stack required object from the stack and deliver it. SMAC is a multi-agent game where we control the team of allies which has to defeat the opponents. In case of SMAC, we instead of using the standard reward payoff, we use sparse rewards where the agent is only rewarded for deaths of the opponent or itself. To understand the effects of spectral normalization in different scenarios, we train four variants of MAPPO. The first one is full SN MAPPO, where spectral normalization is applied on all critic layers. The next one is med SN MAPPO, where spectral normalization is only applied on the second layer or the middle layer of the critic. Last SNMAPPO is where spectral normalization is applied only on the final layer of the critic, and the standard MAPPO where we do not use spectral normalization on any of the layers of the critic. Our major focus is applying spectral normalization only on the critic. In RWARE, we compare only mid-SN MAPPO and standard MAPPO. The results show that mid-SN MAPPO converges a little bit faster, but the final performance is almost the same for both the variants. Next, we compare the performance of all four variants on three super hard SMAC maps. 3S5Z versus 3S6Z shows the performance on an imbalanced team where we see that last SN MAPPO gives the best performance, followed by full SN MAPPO, and then mid SN MAPPO, and the standard PPO version performs the worst. Next, we look at 27M versus 30M, where we compare the performance when the number of agents is very large, which is 27 in this case. Here as well, last SN MAPPO shows the best performance, followed by mid SN MAPPO. Corridor is a special scenario where the agents need to find a specific attack strategy and have to be careful to not be surrounded by the enemy units. Here, we observe that last SN MAPPO and full SN MAPPO perform really bad, whereas mid SN MAPPO convergence really faster compared to the standard MAPPO, even though the final performance is almost the same. To understand the cause of performance gain when using spectral normalization, we compare the gradient norms in the corridor environment and the 27M versus 30M environment. In the corridor environment, we can see that the standard MAPPO version has really high gradient norms, whereas the mid SN MAPPO has relatively more controlled gradient norms. And when we look at the number of dead enemies, we can see that mid SN MAPPO is always having more number of, it has killed more number of enemies compared to the standard MAPPO, even though the win rate is almost the same in both. Now, when we look at the gradient norms of 27M, 30M, we can see that they are already in control. So here we assume that the performance gain can be attributed to the fact that applying SN also scales the gradients. Now, finally, let us look at the benefits and drawbacks of applying spectral normalization. The benefits of applying spectral normalization to the critic are that it helps stabilize the critic by constraining the gradients. Optimization effects by scaling the gradients by the inverse of the maximum spectral value. Better learning of smooth value functions by applying spectral normalization on the final critic layer. Some of the drawbacks of spectral normalization are that spectral normalization only helps to an extent and under the conditions that the agent is able to reach some rewarding states by random exploration. So in the case of SMAC, if we give the reward of only winning or losing the entire match, that is really sparse reward, and even spectral normalization won't be able to help in convergence of the standard on policy algorithms. When applied to final layer of the critic, SN only helps when the value function is smooth. Otherwise, as we saw in the case of corridor, where the value function could have been not that smoother, we see that the last SN MAPPO and full SN MAPPO fails to converge. Some of the future works that we would like to explore are to look at how spectral normalization affects when we try learning a deeper critic. We only applied spectral normalization to the critic layer. It would be interesting to know the effects when we apply spectral normalization to the policy network as well. In our work, we only focus on cooperative multi-agent environments. We would also like to explore the effects of spectral normalization on general sum multi-agent environments. Thank you.